Let's explore the fundamental operations on sets. In this lecture, we will discuss the common binary operations that are applied to sets to create other sets. And to be clear, a binary operation is simply an operation with two inputs, specifically a left operand and a right operand. The key operations we will study are union and intersection. Almost all other operations are derived from those, but we will also cover difference and symmetric difference. Understanding these operations is essential because they form the foundation for reasoning in mathematics, logic, and computer science. The first core operation, the union of two sets. It is the set of all elements that are in either set. And remember, sets do not contain duplicates, so that way when you combine two sets, the duplicates are not written twice. Think of it as combining everything together. It's the operation where we just compile two sets together to make one big set. For example, if A is the set containing the numbers 1 and 2, and B is the set of numbers 2 and 3, then the union of A and B is 1, 2, 3. Notice that 2 is still only there once. The intersection of two sets is simply the set of elements that they have in common. It only contains what overlaps the two sets. For example, if A is the set 1, 2, and B is the set of numbers 2 and 3, then the intersection is just simply 2. Now, if they don't have any elements in common, the result will be the empty set, but it will be a set nonetheless. The difference between two sets is what is left in the first set after removing anything found in the second set. For example, if the set A is 1, 2, 3, and B is the set of numbers 2 and 3, then A minus B is simply just 1. Notice that all the elements of B were removed from A. The symmetric difference of two sets is simply the set of elements that are in either set, but not in both. It removes the overlap and keeps the differences on each side. For example, if A is 1 and 2, and B is 2 and 3, then the symmetric difference is the set of numbers containing 1 and 3. Notice that 2 has been removed because it's in the intersection of A and B. Now let's look at subsets with these operations. If B is a subset of A, then the union of A and B is just simply A. And the intersection of A and B is just simply B. We'll do more demonstrations of this later, but notice that I have an example up here to where we kind of have an inert operation when we do unions and intersections depending on which one is the subset. Just like in arithmetic, sets also have distributive properties. The first law says that intersection distributes over union. That means A intersect with the union of B and C is the same as calculating first A intersect B, and then calculating A intersect C, and then calculating the union of those two results. The second law is similar, except that it says union distributes over intersection. Let me take a moment to go to my notebook, and I will demonstrate a few examples of what we have discussed. So remember, whenever these operations are happening, we're going to have a left operand, we're going to have a right operand. Both of these are sets, and the result will be another set. So anytime we take one of these operations on two sets, the result will always be a set. And we'll demonstrate how this may be the empty set, but keep in mind, the empty set is also a container that has nothing in it, but it is a set nonetheless. Let's first consider union. Let's define A to be the set of elements 1, 2, 3, 4, and 5. And then now let's suppose B is the set of numbers 2, 4, 6, 8, and 10. Now when we do the union will be written like this: A union B. And in set better notation, this is simply the set of elements X such that X is in A or X is in B. Now it's important to realize that we say the word union for the symbol, but what you probably should understand is that it's closely related to the OR operation, as we know it in grammar and in computer science. Okay, to give a concrete example, in this case, A union B is simply all the elements combined, but remember, sets do not have duplicates, so you're probably better off just rewriting the first set exactly as it appears. And then you go to the other set and you'll say, iterate through the elements, you'll say, is 2 already in there? It is, so I don't need to write it again. Is 4 already in there? It is, so I do not need to write it again. Now we have 6, 8, and 10 that are not in my set currently, but are in B, so that means I need to add them. So we're going to have 6, 8, and 10. Okay, that pretty much summarizes A union B. So let's keep the two sets that we defined earlier for union, and now let's consider the intersection. Let's consider A intersect B. And in set builder notation, this is simply the intersection between the two elements. It's the elements that are in both, so we say that it has to be X is in A and X is in B. And notice that the intersection operation is very closely tied to the AND operation that we know in grammar and in computer science programming languages. All right, great. So to give this concrete example, A intersect B will simply be the elements that are common to both sets. So what I recommend is taking the smallest set. Since they're both kind of equally sized, it won't matter. Just iterate through one and verify that any element's in the other, and then you have it. So you have, is 1 in both? No. Is 2 in both? Yes. Is 3 in both? No. Is 4 in both? Yes. Is 5 in both? No. And then you basically stop there. So keep in mind that I basically iterated over set A, checking each element to see if it was in set B, and if it was, then it's in the intersection. Otherwise, it's not. Let's suppose that we have A, in this case, is 1, 2, 3, 4, and then set B will be 5, 6, 7, 8. Now, when we calculate A intersect B, keep in mind that we said both the left operand and the right operand are sets, but the result will be another set. However, there's nothing in the intersection here. It's completely empty. But that doesn't change the fact that an operation on a set should create another set. So since we're going to have a set with nothing in it, this is our classic empty set. Now consider set difference. So with set difference, you essentially have one set, and you're going to remove elements from it that appear in another set. So there's two ways to represent this. We have A minus B, and we also have A take out B. These are two ways to represent the same thing. It is the set of elements such that they are in A, they have to be in A, but they cannot be in B, and X is not in B. Okay, so what that means is, if we take a set, we're essentially removing elements from it that appear in another set. If that set has other elements that are not in A, we don't care about them. So let's give a concrete example. So A, let's let A be the set of numbers 1, 2, 3, 4, 5, and 6. And let's suppose B is a set of numbers 2, 4, 6, 8, and 10. Okay, so now when I calculate the difference of this set, I'm going to iterate through set A. And I'm going to check to see if that element is in set B. If it's an element in set A but it's not in B, then it will go in this different set. If it's in A but it's also in B, then it will not be included. 1 is in A but it's not in B, so it goes in here. 2 is in A but it's also in B, so it doesn't go in there. The next number that's in A but not in B is 3. 4 is in both, so we can't put it there. 5 is only in A, so we put it here. And 6 is in both, so we don't write it. Now notice that 8 and 10 are also in B, but we don't care. It's only the elements in A that do not appear in set B. Keep in mind that a lot of operations are commutative, but in this case, this operation is not commutative. Similar to subtraction, A minus B is not the same thing as B minus A. Completely two different sets. Symmetric difference is kind of where we're looking at what happens when we remove the elements from the intersection. So it's basically a union, but we remove the intersection. So symmetric difference, it's typically represented with this triangle notation. We'll say A, symmetric difference, B. Okay, and in set builder notation, this one's kind of interesting because we're using the other operations to build up this operation. It means X is in the union of A and B, and X is not in the intersection of A and B. So to give a diagram, this is what it's going to look like. We're going to have all the elements in A. So let's suppose this is A and this is B. We're going to have all the elements in A. We're going to have all the elements in B, but we're not going to include anything in the intersection. So these things in red are not part of that. All right. So the symmetric difference is usually the one that people have a little bit of struggle, maybe trying to internalize what it's doing. But basically, you take the union and then remove the intersection, and you have it. So to give a concrete example again, let's say A is equal to the set of numbers 1, 2, 3, 4, 5, and 6. And let's suppose B is equal to 2, 4, 6, 8, and 10. The symmetric difference between the two sets is basically this. We look in there, we're going to combine everything, and as long as it's not in the intersection, we could do it. So one trivial, maybe naive way of doing it is just iterate through both A and B and making sure that the elements are not in both. So 1 is in A, but it's not in both, so it goes here. 2 is in both, so it doesn't go in here. 3 is only in A, so it goes in here. 4 is in both, so we discard it. 5, it goes in here. 6 is in both, so we don't write it. Now we go through B. 2 is in both, so we don't write it. 4 is in both, we don't write it. 6 is in both, so we don't write it. But 8 is only in B, so it goes in here. And 10 is only in B, so it also goes in here. So that is what we refer to as the symmetric difference. Sometimes set operations can appear somewhat inert or degenerate whenever we take a set and apply the operation on one of the set's subsets. And notice very clearly that B is a subset of A, and this is the classic way of writing it. Well, the union of A and B, that would be where we effectively do what? Combine the elements of A and B, and then we don't have duplicates. But if you notice, I would go through and I'd write all the elements of A. So 1, 2, 3, 4, 5, and 6. And then I would go through and add the elements of B, but ignore the duplicates. But everything in B is already in A. So effectively, this just becomes set A. Whenever we have this and it simplifies to something degenerate like this, we would just say we get A back. Now let's consider the intersection of the two. Now we may be able to move a little bit quicker because I think you guys see where this is headed. A intersect B is all the elements that are in both A and B. Well, since B is a subset, doesn't that basically mean that, say, this is just set B? Okay, now what about A take away B? So this would effectively be all the elements of A, but we remove the ones that are also in B. And so this one is not really degenerate. It actually creates this set. 1, but not 2. 3, but not 4. 5, but not 6. But let's reverse it whenever we talk about removing the superset from the subset. The difference of two sets is not a commutative operation. A minus B is not the same thing as B minus A. All the elements of B, but we remove the ones in B that are also in A. But every element of B is in A, so that would effectively mean we're removing all the elements of B completely. Asymmetric difference B, this would be all the elements that are in A, union all the elements that are in B, but then we'd take out the intersection. So we would go through and maybe look at all the elements of A. 1, is it in both? No, so we put it. Is 2 in both? Yeah, so we don't put it. 3, it goes in here. Not 4, but 5. And then 6, no. And then we would go through B and making sure what elements are in it, but not in A. But we don't have to care about that because all of the elements of B are already in A, and so the intersection will be removed. But notice that it ends up being the same thing as A minus B. So that is basically what happens when you apply these operations to a subset. It is important and it's very common to consider these things in mathematics. Let's talk about the distributive laws. So imagine that we have A union the intersection of B and C, and we're writing like this. All right, so let's give a concrete example of what this will look like. So let's suppose that A is equal to the set maybe 1, 2, 3, 4. Let's suppose that B is the set 3, 4, 5, and 6. And then let's suppose that C is the set 3, 4, 5, 6, 7, 8, and 9. Okay, when we go through this, A union B intersects C. B intersects C would be the set containing the numbers 3 and 4, 5, and 6. Okay? And then we're going to take A and we would union this together. So we'd have 1, 2, 3, 4. And we take the union of that. So what the result would end up being would be this. The union of these two sets would be 1, 2, 3, 4, 5, and 6. But what we would find out is that this would be identical if we were to take A union B, and maybe we'll put parentheses just to make sure we're very clear about this, and we would say intersect A union C. Okay, so what I'm going to do is I'm going to rewrite this down here, and I will put this here 1, 2, 3, 4, 5, and 6. And I'll erase this, and we will actually compute this right-hand side the same way. So we'll have A union B. So what is that? That would be the set of numbers 1, 2, 3, 4, and then we would add 5 and 6 to it. And then we would intersect this with the set A union C, which would be 1, 2, 3, 4, but we'd also be adding 5, 6, 7, 8, 9. 5, 6, 7, 8, 9. And then we close that off. And what we'll see is that when we take the intersection of it, it will be basically just the set of numbers 1, 2, 3, 4, 5, and 6. And so notice that the result that we got here is exactly the result that we got here. When we say the word distributive, remember back when we used to say 2 times 3 plus 5? That'd be the same thing as distributing this 2 to here, and then putting the plus sign between them, so it'd be 2 times 3 plus 2 times 5. So notice that this times operator is the one that gets written twice, and that this plus sign is the one that gets written once. So in this case, this will be written once, and this will be the one that gets distributed over both of them. A union B, A union C, and then take the intersection of the two. So it's A union B intersect A union C. In the previous example, we said that union distributes over intersection. Well, it turns out that it works the other way too. So if I say A intersect B union C, it turns out that we'll distribute this A here and this A here and make this the common operator between those two things, and then make this operator the one that separates the two results. So we have A intersect B union A intersect C. So what we want to do is maybe give an example of that. So let's suppose that A is equal to 1, 5, 8, and 9. Let's suppose B is equal to 2, 4, 5, and 6. And let's suppose C is the set containing the numbers 3, 5, 7, and 9. So first, what are we calculating? A intersect B union C. So A intersect B union C. So first, we're going to take the union of B and C because parentheses goes first. So it's going to be the set, 2, 4, 5, and 6. And then we're going to add 3. 5's already in there. We add 7, then we add 9. Over here in A, we just basically rewrite it. It'll be 1, 5, 8, and 9. but we're going to take the intersection because now that we've got this result, because what is this one? This is B union C, and over here we just have A. Okay, so walking it down a bit, we find the intersection, not 1, but it's going to be 5, not 8, but 9. So we have that complete. Well, let's go over here and let's compute what it would be when we have A intersect B union A intersect C. So we're going to have A intersect B union A intersect C. Okay, so first, what is A intersect B? Well, this will be the set containing the numbers not 1, but 5, not 8, nor 9. So that's basically it. And then we're going to take the union, and what is A intersect C? It's going to be A intersect C, so it's not going to be 1, but it will be 5, and it will be not 8, but 9. And then when we take the union of these two things, it's basically combining them together, only without the duplicates. And so this becomes the set 5, 9. And so notice that these two things are equal, showing that these two things are equal. All right, so this shows that union distributes over intersection and intersection distributes over union. So that concludes my demonstration of examples. So to summarize what we've learned, union combines sets together. Intersects finds their overlap. Difference finds what remains when one set is after removing another. Symmetric difference, it removes the overlap and keeps what's unique. All these operations represent things that we would actually consider in our everyday lives, except we're formalizing them in mathematics. I want to thank you for watching this lecture, and I also look forward to your comments. If you have a comment that's positive, please post it because it helps me understand what's working out well. If you have some suggestions of where things could be improved, please let me know and I will consider them in future lectures. Thank you for watching and have a great day.